The formal part of the class will start at about 9:05, but I'll just start with some introductory remarks. First of all, I've got bios from a large number of people. I haven't done a count yet to see from whom I haven't gotten them, but if you haven't sent me a short bio, please do. It just helps us to get to know who you are. Let's see. Second thing, the next deliverable, which is, I think, in a week or so. I don't have the syllabus with me right now. We'd like a preliminary indication from you of. I'm leaving it up to you to form your own teams. Roughly, we've found about 4 people make up a good team. That's a good way to spread the work around. If any of you are having difficulty or whatever, let me know. We'll try to help. But you know, you're almost all graduate students. You can organize yourself. With preliminary indication of what system you would like to do a study on. Julianne, take a handout. Second thing, yeah. I will be happy to do that. I'll post that. Let's see. The second thing, there's a fair number of listeners in the class, and quite a few of you have contacted me to make sure that it's okay to be here as listeners. I have no problem with that. The only thing that I would ask, right now we're more or less filled to capacity. As long as it remains, I expect that the class isn't going to grow after this, so I think we're okay. What I did tell people is that if we get into a seat crunch, obviously the people who are taking the course for credit have priorities for seats. So any of you who are listeners, please keep that in mind. Next thing, I'm going to be putting some things on reserve in the library. This is courtesy of Professor Cohen. This is the proceedings of a Space Shuttle Technical Conference. Aaron, do you want to say something just about the background?
The background is that we decided after the shuttle had flown a couple of times that we would have a typical NACA, going back to the NACA, but this was NASA technical conference, where we actually had technical papers written by the various people that designed the system. Some of you will hear talk, some of you won't, but these are technical papers of how the systems were developed. So it's a pretty detailed understanding of the thermal protection system, the main propulsion system, so forth and so on. So it's a pretty good documentary of how it was done.
So this should be a good reference for your papers. It's 1983. So like I say, I will go down this afternoon and put this on reserve in the library. I will also put on reserve a copy of a systems study that was done at Texas A&M for a similar course that Professor taught on systems engineering in the space shuttle, just to give you kind of an idea of what someone else did. This was a rather good paper. I see you gave them a very high mark, so it's presumably that means it's a good example. Finally, you've all got a copy of this paper by Professor Cohn and Milt Silvera, who was also a very responsible person in the shuttle program. It's a high-level background on the shuttle and its systems. I'm sure there are some of you here who are space enthusiasts and who probably have followed the shuttle system pretty closely, and to whom there won't be a whole lot new here. But on the other hand, we want everybody in the course to come up to a certain level of knowledge about the shuttle, its systems, and the systems engineering that went behind it. So I think it's good to have something like this available. It's a nice reference piece. Okay, the next today and Thursday, Professor Cohen is going to give an introduction into the shuttle, its systems, and the system engineering that went into it. Before we start that, are there any other questions, either about the technicalities of the course or just anything that... Oh, I know one thing. I had a few comments from people telling me that the PDF files which I posted on the website, some people could read them, some people could not read them. I've been posting... I have Macs, but I've been posting PDF files for numerous courses. I've never had any problem with people reading it before. How many people did anybody, if you've tried, first of all, who has tried to look at the files? Okay, of those people who have tried to look at the files, who has had difficulty? This is strange. Maybe... well, if anybody has any ideas about what the problem might be, I'd be very curious to... I mean, have you ever had this problem with other courses on I will do a couple of experiments and post one or two more documents, both in PDF and in either Word or PowerPoint form. I'd suggest that everybody during the next 2 days go and try to open them, and let's see if we can isolate where the problem might be. Like I said, I've never had this problem with any other courses, and in principle, I mean, the whole point of PDF files, it's supposed to be compatible across Macs and PCs and all that. So I don't know what the problem is, but we'll see if we can run it down. And thanks to those of you who let me know that there was a difficulty. That's all I have. Any other questions, comments? Yeah.
What are you kind of expecting with this journal, these journal deliverables, just so we can kind of be thinking ahead of that?
The idea is to basically put together the highlights of the lecture from a systems engineering point of view. In other words, what we want, and when somebody is talking about a specific system, we want you to have a brief description of the system, the purpose, what it does, something about the design considerations, something about the operations, kind of the basic concerns that from a systems engineering point of view, and anything they talk about, particular interactions between that system and other systems. Can you think of anything else in particular?
I think that's about...
Okay. I'll think that through a little bit more, and maybe I can come up with a checklist that would help you put that together. It's not meant to be a big burden. It's just a way to organize everybody's thinking on how to get the most out of the lectures, particularly because, as I mentioned, these lectures they're all being given by and large by different people. They'll have different styles. We've kind of explained to everybody the structure of the course, what we're looking for, but I can't really guarantee in advance what the content of the lecture will be. Professor Cohn and I will make any attempt, if the lectures don't cover some of those critical points from a systems engineering point of view, we'll try to stimulate the discussion on that or fill in. But you should do the same thing. In other words, make sure that if there's something that you think you would like to be getting out of the lecture and you haven't gotten, don't be embarrassed to ask questions.
I think something you ought to think about when these individual lectures come up should be the description and function of the system. If they don't bring that out, then we ought to try to bring it out. The requirements of the subsystem of the system. What are the requirements? Because that's very fundamental. What are the requirements? The development of the subsystem. What kind of problems do they have? What kind of technologies do they have to overcome? And of course, the operation of the subsystem. So those are, I think, key points. Now, whether you're going to get that from everybody or not, I don't know. But I think you need to look for that. And if you don't, then we'll try to develop that.
Yeah.
Are you looking for just the notes we take in class, or
I don't follow you. I mean, I'm not looking for a Xerox of what you're writing in the notebook, if that's what you mean. No, I mean, I'd like you to put your thoughts together into a concise form, and I think that will be a good reference for you, hopefully after the course on shuttle systems. Okay, over to you.
You're going to have a very unique opportunity. You're going to have people speak, lecture you on the various shuttle subsystems in quite a bit of detail. You'll have some people that will be very, very positive about the shuttle, that think it's a great design, a great operation. You'll have others that will not think it's so good. And you'll have some that will give you just a detailed technical approach of what happened. I think what I would like to suggest to you, for your good and for the good of the future students, future designers, that you ought to come up with your own decision. Was it the right design? Was it the correct design? Should it have been done differently? And if so, why? And how would you do it? And I think that'll be good for you after you get to work on when you go to work on future projects. It'll also be good, I think, for NASA, something we could turn over to NASA. So I think it's a very valuable thing to do. So I would suggest you do that as you go through the course, and I will be happy, very happy, to talk to you about any of your ideas that you have through the internet, through emails, or in personal discussions. So, and you might want to do this later on as the semester develops. A little bit what I'm going to say today really starts off from where Dale Myers, your previous speaker, left off, and it gets a little bit more detail. So it's going to, as this course develops, you're going to get more and more and more detail. But let me start off again, just very much like Dale did, and talk about the shuttle history. In 1952, fully reusable launch vehicles, the concept was discussed. People were interested in that. In 1962, fully reusable vehicles were seriously considered. The Air Force studied Project Dinosaur, which was canceled in 1969. In 1969, NASA adopted the idea of a fully reusable spaceship. I became the Orbiter project manager for NASA in August of 1972. And at that time, I also was manager of the Systems Engineering Organization for the first 2 years. So I had the total, you might say, the total system at that time and the Orbiter in 1972. Yes?
Could you tell us a little bit about your background that got you to that position?
Well, my background was that, I started off at, I graduated from Texas A&M University in 1952 and went to the Army, went to Korea. And then when I came back, I went to work for RCA, and I worked on the microwave tubes, the microwave oven. In fact, when I told my wife what I was working on, I said, I'm working on a microwave oven. That was in 1954. That was a long time ago. How many people have microwave ovens today? Everybody does. Well, 1954, 1955, when they came out, they were about $3,000 a piece. I was working on one. I told my wife, and we've been married a long time, I told my wife that I was working on something called a microwave oven, and we were going to be able to cook a roast in a couple of minutes, and a potato in a couple of minutes. And she looked at me and she said, that'll never sell. So anyways, that's what I worked on. Then I worked for General Dynamics on the Atlas and Centaur. And then in 1962, I went to the Johnson Space Center and worked very closely on the Apollo program. I worked very closely with the MIT Instrumentation Lab, now the Draper Labs, on the Guidance, Navigation, and Control System. I became head of systems engineering in Apollo, then manager of the Command and Service Module in Apollo. Then I became in August '72, I became the manager of the Space Shuttle Orbiter. Then I became director of research and engineering at Johnson Space Center. And then I became director of the Johnson Space Center. And then I became, for a while, I was acting deputy administrator in Washington. And then I retired and went to Texas A&M to teach. And then Jeff asked me to come do this, and I'm very happy to be here.
Thank you.
Okay.
Actually, one thing that you mentioned reminds me of something which, not to divert the lecture today,
That's
but
right.
the fact that there was specifically a systems engineering group
That's
at
right.
the center, which was separate from the project
That's right,
offices,
that's right.
is something which is probably worth talking about at some point.
Well, let me just make a mention of that. In Apollo, when we were in Apollo, we sat around the table for many days and months trying to figure out how you define systems engineering. We really didn't know what systems engineering was. In fact, today, I'm not sure you'll get a clear definition of what it is. I want to give you some examples as we go through the lecture. I'm going to give you some examples of what I think it is and how it was used. So we'll do that.
Let me say just one other thing.
Sure.
Professor Cohen has these view graphs in electronic form down in Texas, and when he gets back, he'll send them to me, and I will post them on the website.
Well, I'll give you this whole package because there's also some pictures. I don't know what you want to do with the photos. Something that's very key in any design, and something you really need to pursue whenever you do a design project, is understand the requirements. Because if you don't understand the requirements, you made a very good product that's useless. So you got to understand what your customer wants, the top level requirements. One of the things that was handed down to us, it was supposed to be fully reusable. That was one requirement. 14-day turnaround time. You were supposed to be able to turn the shuttle around in 14 days. Deploy and retrieve payloads. You have to deploy a payload and you had to retrieve a payload. Design and development and test is estimated to be $5.1 billion in 1971 dollars. Dale Myers didn't tell you the whole story, but one of the reasons that Dale Myers and I are such good friends, he was associate administrator of manned spaceflight. I was the orbiter project manager, and they being headquarters is always there to help, actually took away 2 years of inflation. If they had given us those 2 years of inflation, we would have met the $5.1 billion in 71 dollars. And Dale fought for that but lost. Here's where we missed it. The original cost per flight for 65,000 pounds was $10.5 million per flight in 1971 dollars, but for a flight rate of 60 flights per year. When I told my wife I was doing that, and she's been around the space program a long time, said, "You never agreed to that, did you?" But 60 flights per year is pretty hard to do. But that's what we came up with at the time. Now, Dale mentioned the Air Force requirements, but here was the Phase A studies. The Phase A studies were conducted to determine the basic requirements and their effects on design in 1969. The principal issues were the size and weight of the payload, the cross range of the orbiter, and what kind of heat material were you going to use. You got to recognize that the heat resistance, we're going to use heat resistant structure or reusable insulating material. You got to recognize that our background was a Mercury, Gemini, Apollo, and they all used an ablative material. And ablative material cannot be reused because basically the surface changes. You had to have some kind of insulating material so the surface did not change. Let me now go through very quickly for you, just for the sake of completeness. Dale showed you a few of the studies. I want to flash up a lot of studies, Phase A studies, and just to let you take a look at what people were doing. And you don't have to read the words, but you might just look at the diagram. Theirs was General Dynamics Phase A study. There was North American Rockwell. That's one Dale was talking about because that's where he was. And there was Phase B study for McDonnell Douglas. So that's what they all looked like at the time. I'm going to go through some, and then just for the sake of completeness here. There was, again, another McDonnell Douglas study, Martin Marietta, and the last one was, that was Martin Marietta. So those were basically some of the studies. So you can see they all had some kind of a wing-type vehicle. However, there were...
Already most of those were delta wings, so the decision had already been made.
Probably the decision already made, cross-range. Now, interestingly enough, and I'm going to quote some names to you, and you might go back and research it. Max Faget was like the lead engineer. He was sort of like just a sort of a man that was moralized in terms of the space program. He felt we ought to go with the straight wing, which very, very strongly about a straight wing, but that eliminated the very large cross range that the Air Force needed. Straight wing was easier to build, not as high loads on it, and so forth. Here, interestingly enough, if you look at Chrysler. Chrysler had a study, and Chrysler actually had a capsule. So Chrysler had a capsule, but here were more vehicles, see? And people were really thinking about this time of a flyback booster, where you actually had a booster that returned and came back and landed, and then also had a manned vehicle that landed. So that's what the real requirement was at the time.
Somebody sort of commented about Chrysler, you know?
Yeah.
There was also Ford.
Ford Aeronautics.
I mean, there were a lot of aerospace companies back in those days.
Yeah. It's changed a lot, that's right. And here's McDonnell Douglas, of course, Grumman. So a lot of these studies, then you're getting to see something already start to look a little bit like the shuttle. I'm almost through. I know this is... And here's more. These are, I think, getting maybe into the Phase B studies. But you can see some of them are starting to look like the existing shuttle. Lockheed. Okay, so now the shuttle studies, the principal issues in the shuttle studies, now we're starting to get a little bit more technical and a little more detailed, is should the reaction control system, now the reaction control system is basically a propulsion system that controls the vehicle about its center of gravity. It's for attitude control, basically. So should the reaction control system be liquid oxygen, liquid hydrogen, or should you use a hypergolic system, where it's a storable type system? That was a big issue at the time.
Everybody here know what hypergolic fuel is? Let's talk about it a little bit.
Well, hypergolic fuel is a fuel that actually, like hydrazine, it actually does not need it's actually got an oxidizer and a propellant in the same fuel. Now, the other one was a fly-by-wire flight control system. That was a big issue. Do we have a fly-by-wire flight control system? And now everything has a fly-by-wire. All the military jets have a fly-by-wire. But basically, was it going to be a digital computer control system, or were we going to have cables fly the machine? That was a big issue, a very big issue at the time. Wind tunnel test determined wing size and configuration. That is a very difficult thing to do. But this is starting to get into what you might say is systems engineering. This is starting to get into what you might say is systems engineering. Air-breathing engines were considered for flyback and later determined to be too heavy. And some shuttle studies that still had to be done was the entry techniques, landing speed, what type of landing speed were we going to have, and the approach pattern. So these were some things that had to be understood during the studies. The Phase B studies, were performed in mid-1970s to determine the preliminary design. The results showed a fully recoverable orbiter, disposable fuel tank, parachute recoverable solid rocket boosters, high-performance hydrogen-oxygen engines placed in the orbiter to be recovered. This was all systems engineering that led up to the design. So you have systems engineering in various phases of the program. And usually systems engineering composes of an interdisciplinary team that has been given some assumptions, some constraints. They have some top-level requirements. They do an iterative process with some tools such as computer tools for calculation of loads and flight mechanics, and they come up with an iteration of what the design is going to be. So that's basically how it was done. Now, some of that was sort of like the ground rules. Some of the things that came out of it, once we started putting the total system together, we showed that the fully reusable with a flyback booster was greater than $5.1 billion. So that was thrown out. Now, there is a question, and that's what I asked Dale. Should we have said, hey, we need money to really have a flyback booster? But they gave us a constraint of $5.1 billion in 1970 and it didn't make it. And I showed you many configurations were studied, and the turnaround time of 14 days dictated a landing with a winged vehicle on a runway. You weren't going to be able to land this in the water or with parachutes. You were going to have to land it on a runway so you could quickly turn it around in 14 days. The payload deployment and retrieval requirement determined the location of the orbiter on the launch configuration. Because if you look at that large payload bay, it'd be very difficult to put that on top of the vehicle. One of the requirements that NASA has now, that the CEV should be on top of the stack. Well, if you're going to have that large a vehicle, it's pretty hard to put it on top of the stack.
And particularly with wings.
With wings, yes. So this is what we had to come up with. This is some of the results of it. And these are all system studies. This is systems engineering. Now you're getting to look at what the design is starting to look like. This is the agency commitment in March of 1972. In May of 1972, you had the North American proposal, and then I became Orbiter Project Manager in August of 1972. We did a study, and PRR is the Preliminary Requirements Review. But that was the configuration. We made some changes, and the production commitment was made in May of 1973. This chart is not, it's sort of a gee whiz chart at one point in time, which showed the $1971 cost per flight for the Thor, the Atlas, the Titan 3C, the Saturn 1B, and the Shuttle. And that's payload to orbit. So you can see that the thing that was really missed in the Shuttle was the $10.5 million cost per flight. Yes, sir.
What is the notch on top of the second two that disappeared in the production?
Let's see. I'm sorry. Oh, that up there? That was an air data probe. That was taken off because it wasn't needed. Okay. Good question. Thank you. And by the way, don't hesitate to interrupt me and ask me questions anytime. And if you don't understand what I'm saying, please stop me, tell me to slow down, or ask me any questions you'd like to ask me.
There are air data probes on the
Shuttle.
but not on the tank.
Okay, major configuration decisions.
And by the way, you don't see them on the shuttle because they're inside the thermal protection system, and they're only sort of turned outwards to take data when you get down to about Mach 3 and you're through the heating. Otherwise, they would burn off during
Now, in the approach and landing test, they were out front.
Yeah.
Approach and landing test, when we separated from the 747. I'm going to tell you that story in a minute. Okay, here's some of the major decisions. We were going to go with a hydrogen-oxygen main engine. This size, now, that's one of the system problems you have to decide. Once you decide what kind of propellant, what kind of engine you're going to use, that basically sizes the external, the tankage. And I'll show you that on another chart. But this, as I said, this size, the liquid oxygen hydrogen tanks, which is not reusable. And I'll make that point to you a little later on. But once you decide what kind of engine you're going to use, that sizes the tank because of the using the equations of motion. I'll get your equation. You can figure out how much propellant you need. You get the density of the propellant, and now you know what size tank you're going to use. Yes, sir.
A couple slides back, you said the main engines of the orbiter had to be recovered.
Right.
That wasn't separate from the orbiter, though, was
It was a separate contract, but it was placed inside the orbiter. So when the orbiter came back, the engines came back with it. Was that your question? It was, for example, the Johnson Space Center was responsible for the orbiter, and you're going to have the person talk that was responsible for the engine, J.R. Thompson, and he was the director of the Marshall. He was at the Marshall Space Flight Center, but the orbiter was installed. That the engines were installed in the orbiter, so the orbiter brought them back. Solid rocket boosters provide the additional propulsion required to get the orbiter in orbit, and the solid rocket boosters were designed to be recoverable and reused. So those were some of the system studies that led to the configuration. Yes, sir.
At that period, was there any discussion of the environmental impact of solids being used at 60 flights a year?
Yes, there was. There was quite a bit. There was quite a bit. I don't recall the details, but I do know there was a lot of work going on that many solids being used. And I guess we basically put that to rest, but there was a lot. I don't know the details of it. In fact, that might be a good question. If you're not here, we'll ask J.R. Thompson, because J.R. should know that. I mean...
When I met with some of the Russians who worked on the Buran, which was the Russian copy of the Shuttle.
Right.
One of the big changes was that they said, how could the Americans have used solids?
For that many flights. It was studied and actually put to bed, or put to rest, should I say. I don't know the details, but it's a very good question. That's something I think they're going to be very speakers, as I said, and JR should have that answer. Solid waste is recoverable and reused. Well, some of the things I've said before, the arbiter decisions, the arbiter entry cross range required delta wings. To go 1,100 nautical miles cross range, you needed delta wings. Deletion of the air-breathing engines for moving arbiter required the Boeing 747 to carry the arbiter. Let me tell you that story. All of you are very familiar now that when we landed at Edwards Air Force Base, we put the arbiter on top of the 747 and we ferry it back, fly it back to Kennedy. Well, I was the arbiter project manager, and I became arbiter project manager in August of '72, and I was having all sorts of problems. The first thing they did to me was they cut my budget in half. The OMB cut my budget in half. So that was the first thing that happened. And then I just had a lot of problems. So, but I had worked on the Apollo program. I had a lot of friends in the organization, although I was arbiter project manager. 3 of my friends came into the office one afternoon, I forgot, maybe 2 or 3 months after we started, and said, "Aaron, we got a great idea." I said, "What's that?" He said, "We can put the arbiter on top of a 747 or a DC-10 and ferry it and fly it back to Kennedy from Edwards Air Force Base. We may have to make 1 or 2 stops, ferry back." I looked at him for a moment. I said, "That is absolutely the dumbest idea I've heard in my life." And I basically threw the people out of my office, and they were my friends. Well, these people will not take no for an answer. Happened to be they had another very good quality. They were all world-class model airplane builders. I mean, these guys had won competition all over the world, 3 of them. So they came back about 10 days later, said, "You know, I don't know how many have seen the Johnson Space Center, but we have a lot of acreage out there, Texas." And they said, "Come out, we want to show you something." They had built a radio-controlled model of the 747 and an arbiter, and actually flew it for me and separated the arbiter from the 747. So that's how it got started. That's how, and so we eliminated the air-breathing engines. But I remember throwing them out of the office. 5-bar wire with a digital autopilot. Yes, sir.
Are you saying that if you had air-breathing engines, the orbiter itself would fly back?
Yeah, that's a good question. I missed that point. Let me explain to you. If you recall, that's exactly right. When the arbiter lands, you know, the landing gear, the nose gear is very short, so it's sitting there. What we had to do, you asked a very pertinent question. We had to actually replace the landing gear with a different landing gear that caused the arbiter to have an attitude like that. We put air breathing like this, so it wasn't like this, it was like this. We put air breathing engines on, and we took off, and we had to have 5 in-flight refuelings to get from California.
Strap-on air breathing engine?
Yeah, and plus a different landing gear. And we took off horizontally, and 5 in-flight refuelings to get from California to Florida. So that's the real, and you really brought up a pertinent point that I left out. That's the reason why we changed it. Thank you very much. And of course, we went with the fly-by-wire with a digital autopilot. This was a very fundamental change. The astronauts at that time did not like this very much. Now, when you get all these new pilots in, they wouldn't know, what are you talking about, fly-by-wire? Why not have a fly-by-wire system? But they didn't like it at one time. But we went with the fly-by-wire with the digital autopilot. I'm going to talk a little bit more, even though you're going to have a special briefing on the guidance, navigation, control system. I'm going to talk a little bit more in detail about that because that happens to be my expertise. So I'm going to talk about that a little bit more detail. Yes, sir.
What does fly-by-wire mean?
It means that you actually have a computer actually controls the surfaces.
Okay.
Whereas in an airplane, in past airplanes, your stick actually had cables that controlled the surfaces. So you get a lot more performance out of it. I mean, okay?
It's a little bit confusing in the sense that a wire, you might don't think of it as a hard wire, which is like the old type of an airplanes where there was a cable.
Right.
So when you pulled on the stick, there was actually a cable which went back to the ailerons and the rudder and everything. And you know, as Professor Cohn says, everything now has a computer in the middle, and what you're really doing is flying the computer, and the computer then issues the commands to the hydraulic system. But that was, the shuttle, I guess, was the first
shuttle was the first
vehicle that really had that system.
That's right, exactly.
There were no commercial planes flying with that system.
Or military planes flying.
Yeah, I mean, they...
Yeah,
So it was, and you know, the real concern was safety and reliability.
That's right.
You know, suppose you have a computer problem, what are you going to do?
I'm going to talk about that in detail, but that's a good question. Any other questions? Those are very good questions. I appreciate it. Yes, sir. Cross range, basically, you realize the orbiter is a glider, so to speak, a glider. Not much of a glider, but a glider. And it actually, downrange would be going in this direction. Cross range would be out of plane, basically, out of plane direction. So you can actually maneuver out of plane.
We've got a nice globe here. I'm not going to carry it up to the front, and I don't have a piece of chalk either, but...
Here you go, Jeff. Jeff, there you are. Good. These are very
okay.
good questions, by the way. Thank you very much.
Okay, so, here's the U.S. roughly. So this was designed for the military requirements, okay? So they wanted to be able, for reconnaissance satellites, basically, you want to be in polar orbit because you're going around, let's say this is an orbit here, and then the Earth turns underneath it, and so you basically fly over all parts of the Earth. So that was the basic military requirement. They wanted to be able to launch out of Vandenberg on the west coast into a polar orbit. And because of security reasons, they this sounds a little bit strange when we think back on it, but you wanted in a time of crisis, remember we were in the Cold War and everything, you wanted to be able to put a satellite up without necessarily giving the other side a chance to make all the radar measurements on the shuttle and everything and figure out right away where the satellite is. And also there might be hostilities, they may be, the shuttle was a strategic asset. So basically they wanted the shuttle to be able to land the very next orbit. Well, all right, you take off from California, you fly over the pole, you deploy your satellite, and by the way, we have never, ever, with all the satellites we've deployed, we've never deployed a satellite on the first orbit. That would be an incredible feat, but that was the requirement. So you fly over the pole, you come back around, now you're ready to land in California, but during that time, the Earth has turned by 1,000 miles, okay? 24,000 mile circumference and 24 hours, and actually 1,500 miles because an orbit is 90 minutes, 1.5 hours. So your orbit now would put you right over the Pacific Ocean. If you just burn your engines, slow down, and come down through the atmosphere, that's where you're going to land. So instead, as you're flying through the atmosphere, you basically have to come down banked on your side, and so essentially you're generating a lift vector, and instead of turning your lift vector up, you turn your lift vector to the side, and that pushes you over. And delta wings can generate a higher lift vector than the straight wings, and that was the determining factor.
Very good.
Jeff or Eric, could you mention the issue of also landing on land in friendly territory as far as cross range?
Well, I think that's right. I guess I'm not sure I can. Can you address that, Jeff? I don't.
My recollection of the time was that even coming in over the Pacific, yes, there are some places where you could land, but it would mean on land, but it would mean landing in the Soviet Union or Eastern Europe, and they didn't want to do that.
Yeah.
So the cross range traditionally was to be able to make Australia.
Well, I'm sure that's right.
There were certainly there were contingency landing sites that we had all over the world.
Yeah, I'm sure that's right. I guess I can't address that.
It could have been a much smaller cross range if we were willing to
land
contingency landing sites in Soviet place.
Yes, I think that's right.
And I will say, continue to remind us if we don't explain some basic things, because we've been dealing with this for so long that some of these things just seem like second nature. And you weren't even born when the shuttle started flying, and so the level of backgrounds is going to be very different. We want to bring everybody along with us. So if there's something that we say, the same thing, the question about hypergolic fuel.
Yeah.
If we use a term and you don't understand it, we'll try not to use a lot of acronyms.
Right.
I can't guarantee that the speakers won't use acronyms. Don't be embarrassed to just stop and say, what does that mean? What are you talking about?
But as we go through the course, you're going to get more detail. For example, you have a total lecture by a man named Henry Pohl, who's going to talk about the reaction control system. He'll give you all the details you want to know about hypergolics and storables, more than you ever wanted to know. So you're going to get more details as you go through, but don't hesitate to ask questions, because it's good for us. It's an interesting story about, let me tell you another sidelight story. My wife we moved to College Station, and my wife is working at a junior college, and in the registrar's office, and she's working with a young lady, and Apollo 13 came out. Well, Apollo 13 happened to be my first project, first mission when I was manager of the Command and Service Module. So I know a little bit about it. In fact, I'm going to give a lecture in Dick Batten's course on the 26th on Apollo 13. But my wife talked to this young lady, and she said, I went to see Apollo 13 yesterday, and she said, it was so exciting. I didn't know how it was going to end. So, you know, so you know, it is a frame of reference. Well, we've talked about this. Size of the payload bay is 60 feet long, about 15 feet diameter. Size of the crew cabin defined to be over 2,600 cubic feet. The payload, as you know, is 65,000 pounds at liftoff, 35 pounds at landing. And what you need to understand is the orbiter is a launch vehicle, it's a spacecraft, and it's an aircraft. And when you look at the two different missions, or two different systems, I worked on Apollo, as I said, very much, and on Shuttle. And there's no question that the Shuttle is the most complicated, much more complicated than Apollo. On the other hand, the Apollo mission is much more complicated than Shuttles. But that's something that, this is something that makes it very, very interesting. This is a very old chart. And in fact, this is the original chart. It comes out yellow. This was the original cost estimate. This was the original cost estimate, and how they rallied up, they totaled up the $5.15 billion. We talked about that, and that was the very original cost estimate done on a cost analyst chart. There were no computers, no personal computers at the time, and but that is a very, in fact, I found that in my files. That's a very old yellow chart. It's hard to believe some of those numbers. On the other hand, I had a gentleman work for me, got his PhD at University of Colorado, and his subject was the cost of the shuttle orbiter. And it turns out that we did, if we had that 2 years of inflation, we really would have made that cost on the 5.15 in 1971 dollars. Now, let me get it.
It only ran over by about 10%.
Right? Yeah, that's right, yeah. Let's now talk a little bit about configuration. I don't know if you can see this chart or not. But this is, now you might say, how did you go from that conception of in August of 1972 to something with all these numbers on it? Now that is this is really a case in systems engineering. And let me explain to you what I mean by that. There were certain assumptions had to be made. One assumption was that in the orbiter it was going to weigh about 175,000 pounds without payload, and you were going to have a 65,000 pound payload. You made that assumption. You had to make that assumption. You also had to make an assumption that you were going to use a liquid oxygen, liquid hydrogen engine. And why did you select that? Today I'm not quite sure that was a good decision, but we did decide. Why? Because the specific impulse, the ISP, or the performance of the engine, was the highest for the liquid oxygen, liquid hydrogen chemical propulsion that we know today. So we selected that. Well, when you use the equations of motion, you integrate the equations of motion, or you use or any other techniques you may want to use. You then show how much propellant you're going to need to get that into orbit. Then you know that liquid hydrogen has a density of about 4 pounds per cubic foot, very low density. So that means this big external tank is mostly hydrogen. It's very, very big volume, and liquid oxygen is about 70 pounds per cubic foot. So that basically sizes your external tank. So that's a system. I mean, it's a very simplified approach, but that's systems engineering, and you do much iteration, because there's an old adage that the devil's in the details. So you keep iterating on that with this expert team, and then you then say, well, that's still not going to be the most efficient way to get you to orbit. So you say you need really a stage system. So you put the solid rocket boosters on, so you don't have what they call a single stage to orbit. You really have more like a two-stage to orbit. And you size the solid rocket boosters, and you determine when they have to come off. So basically, that is how you go about doing the systems approach, using systems engineering to come up with a configuration. Now, that's a very oversimplified way of doing it, or a statement I made. But that's basically how you do it. And these are some of the dimensions that then come out of the vehicle. And I think they're in that handout we gave you also. And it looks like I'm going to take off. I did know that this chart tries to lift off on me. My chart's I don't know what's the best way to do it. So I think those dimensions are, you can find those dimensions, I believe, in that paper that was handed out. But this shows you all the dimensions of the space shuttle system, the solid rocket boosters, the external tank, and the orbiter. Now, an interesting sidelight in this, which I got to thinking about after the Columbia accident, where the foam came off. Of course, the reason why we put foam on was because with liquid oxygen, liquid hydrogen, at those temperatures, you're going to have a lot of ice formed. And when ice forms and comes down and hits the orbiter with the thermal protection system, I'm going to talk about that in more detail, you're going to do some damage. So one solution would be to put foam on the tank to eliminate the ice. And of course, you would assume that foam could stay on the tank. Another solution would have been to not go with a liquid oxygen, liquid hydrogen engine. Go with what we call storables. Of course, they wouldn't have gotten as much performance, and you probably couldn't put 65,000 pounds of payload into orbit. But those are some of the. But so the point of bringing this to you, those are some of the decisions as you go into various projects. You need to challenge the requirements, because the requirements are really going to decide what kind of system you're going to have. So that's really the point I wanted to make. Are there any questions? Yes.
Wasn't it possible to have isolated from the inside, so
well,
the outside was not that good?
That's a good question. One thought at one time was to put the liquid hydrogen tank, or the liquid hydrogen tank, in the orbiter. And that would basically isolate it. You put inside. So, or put insulation on the inside, as you pointed out. Those were thought about. And in fact, I don't recall the decision, obviously, not to do it. But I don't recall the reason why. But when J.R. Thompson comes, I'll ask him that question, but that's a very good question. Yes, there was two things. One, could you put some of this propellant inside the tank, and the other is could you put insulation inside the tank itself? And that was looked at, and I guess it was complicated and very costly to do it that way, but it was looked at. That's a very good question. By the way, these are very good questions.
One thing when you look at this external tank, only the very upper part is for oxygen.
That's right.
Because the density of hydrogen is so low. I mean, all of this part of the tank is for hydrogen. So to have put all the hydrogen inside the orbiter, we would have a very different looking orbiter.
Yeah, you wouldn't have been able to do it. But she really said, could you put insulation inside the tank? I had the other. Yeah. Any other questions? But that's basically how the system evolved. Now, I oversimplified it to quite an extent, but you got to realize there was a lot of iterations. One other key thing, though, when you have a system team, when you do systems engineering, you do it in a team. You usually have different capabilities on the team: aeros, mechanical engineers, electrical engineers. So you have different types of disciplines on the systems engineering team that can help you do that, and then you have a systems engineer that sort of heads it up. But that was the real. We're going to concentrate more on the orbiter, and when we have one of the speakers, he's going to concentrate on the engine and so forth. But that's what the system looked like. The other thing that's interesting, I think, is what the mission profile essentially looked like. And this happens to be for STS-5, but this is the basic mission profile. Now, let me add, before I start that, let me say, this gentleman right here has flown that profile 5 times. And so he's done that 5 times. He can talk much more about it than I can. One time, when I always tell this story, Jeff's probably tired of hearing it, but when I was director of the Johnson Space Center, we had a lot of visitors. So one time I had Mr. James Baker, who at that time was Secretary of State, and Edward Shevardnadze from Russia, who had the same position in Russia at the time. And I took him over to Mission Control as a visit, and put Mr. Shevardnadze down in the seat, in the flight controller seat, and was going to let him talk to the crew. So, not knowing that Jeff Hoffman was on duty at the time, Edward Shevardnadze spoke in Russian up to the crew, and before the interpreter could answer it, down comes this beautiful answer in Russian from Jeff Hoffman. So that really floored the both Mr. Baker and Edward Shevardnadze and me. So that was an interesting story. Here gives you a little profile of the shuttle mission. You lift off and you've reached dynamic pressure, max dynamic pressure, in about 1 minute, about 38,000 feet. That's where you reach dynamic pressure. You have the SRB step in about 2 minutes. You remember in the Challenger action, I believe it happened in about 60 seconds. But in 2 minutes, you get SRB step, and it lands, the SRB landing by parachutes. You have MECO, which is main engine cutoff. The main engine cuts off, and that to me is the biggest issue. But when that main engine has to burn for over 8 minutes, that's taking all the propellant out of that big tank, the liquid oxygen, liquid hydrogen, firing the main engines to get you to main engine. What's the velocity of main engine cutoff? Do you know? It's pretty much orbital. It's almost orbital velocity.
It's within a few hundred feet per second of orbital velocity.
Yeah. And then you get external tank separation. The external tank comes down about 9,000 miles downrange and lands in the Indian Ocean. Then you use the orbital maneuvering system, the OMS engine, the pods on the back of the orbiter. Use that for a very short period of time to get you to do your final tune to get into orbit. Then you have your on-orbit operations, whatever you're going to do. Go out and service the Hubble or whatever. You deorbit with the OMS engine, the orbital maneuvering system engine. You have entry interface at 400,000 feet. And why do you pick 400,000 feet? Because that's where you start sensing gravity. You get about 0.05 Gs at 400,000 feet. And then you re-enter and land either at Edwards or Kennedy. So that's the typical mission profile. Yes?
Why does the shuttle turn whenever it's lifted?
Why does it turn?
Yeah, it turns and it's down, like on the down part.
You mean liftoff?
Yeah.
Well, why? That's a very good question. Let's see if I can repeat that very accurately. The fact is that we used the Apollo launch pad and the ditches for the flame bucket where the engine goes. So in order to get it to the right attitude, we had to make that maneuver. You had to make that roll maneuver during liftoff. Is that what you're talking, the roll maneuver during liftoff? And we had to make that roll maneuver because we weren't in the right orientation. We had to make a roll maneuver because it wasn't oriented correctly on the pad. Now, let me answer your question. The Buran was a Russian vehicle. Well, Dan Brandenstein, who at one time was an astronaut, head of the astronaut office, saw that the Russians made this roll maneuver. And he asked the Russians, why do you make that roll maneuver? I mean, they didn't have to do it. He said, because you do. And so, now that's a true, did you hear that story? Yeah. Did I say it correctly?
I think so.
Yeah. He said, because you do. So that is a good question. So that's why.
There may be one other aspect to it, and that's the question of why does the shuttle actually fly upside down on the way up? And I believe the original decision was aerodynamics, because
right.
the thrust is asymmetric. You have the external tank, and the shuttle is sitting on the external tank, and so the thrust actually has to be through the center of mass of the whole system. So it's actually flying not straight, but it's a little bit skewed. And for aerodynamic purposes, I guess they figured there was less stress. Although recently they've started partway through the launch, they do another roll maneuver, and I think that's for communications.
Yeah.
And I'm not 100% sure when they started doing that again.
I'm not sure either.
But the early part of the launch, when you ride in the solids and aerodynamically, when you go through max Q, you're in much better shape if you're upside down.
Yes. Oh, let's look at this. I'm sorry.
Was there any particular reason for you guys to use a small solid rocket and big liquid rocket? Why didn't you use just as big solid rocket as possible?
Well, big? Minimize
the liquid fuel carriage or something like that?
Well, to use a big solid rocket booster, it's not very efficient. You really have to, that's why many people have studied single stage to orbits. And
let me just ask, are people here, I know we've got a mixture of Aero-Astro and TPP, ESD. Are there people here who have not seen the rocket equation? So everybody is, well, okay. Let me just
yeah, Jeff's good.
Very briefly.
That's very important. That's very important.
If you have a rocket and you want to increase the velocity of the rocket. I mean, that's a critical thing by a certain delta V. You can take the mass of the rocket when you start the burn, which we call m sub I, the initial mass, and the final mass. And of course, the initial mass equals the final mass plus the mass of the propellant, and that equals the exponential to the negative power of the velocity decrement which you're trying to put in, divided by the exhaust velocity of the propellant that's coming out. Now, this is usually phrased in terms of the specific, what we call the specific impulse times gravity, because it's done by engineers and you know.
Yeah, that's right.
So you'll hear the reference to the specific impulse, and the units of that are seconds. But if you multiply that by the gravitational acceleration, it will actually give you the exhaust velocity. Because this is in an exponential, it's extremely sensitive to the exhaust velocity. Whatever delta V you're trying to get out, if you can add a few more seconds to the specific impulse, then the actual mass of propellant that you have to burn in order to create that delta V goes down substantially. Now, for hydrogen, oxygen, the specific impulse is about 450 seconds. For solid rocket motors,
it's about
the specific impulse is on the order of about 250.
250. That's what I thought.
Like
that's what I thought. It was about 250.
Yeah,
it's about 250.
So you know that's almost a factor of 2, and you put that into an exponent. If you try to get into orbit with purely a solid rocket motor, you need a lot more propellant, and that means the mass that you're able to, payload mass you can take into orbit, is reduced. That's why, in addition to using hydrogen and oxygen, and you know we'll have some a lecture specifically on the main engine, but I mean they got every last ounce of performance out of it. You know, by running it. You know, you'll hear references to running it at 104% of rated thrust, 109% of rated thrust, and all of these have engineering consequences, because in order to increase the exhaust velocity, which of course if you do that, that's in the denominator, so that's going in the right direction, you have to increase the chamber pressure, the temperature, and all of the design problems.
He's going to ask you the question, why don't you use liquids all the way? I knew his question. I knew what your question was. Why don't you use liquids?
That's more higher performance and easier to control and so forth. So my next question would be, why did you want to use a rocket to create the multiple components to the separation?
Well, but why don't you use the liquid hydrogen engine all the way rather than using solid rocket boosters?
Well, the principle, first of all, you know, why not just have a bigger fuel tank, one big fuel tank, and just use the shuttle engine?
That's what he said.
That would be essentially single stage to orbit.
And that
I'm not going to spend a lot of time with the rocket equation, but the delta V that you need to get into orbit is, well, orbital velocity is just under 8 kilometers per second, but to that you have to add
gravity
loss and a drag term, and so the overall delta V is a little over 9, effectively about 9 kilometers per second. If you put that into the equation, it actually, you can get the ratio of the final to the initial masses, and even for a hydrogen-oxygen engine, you can basically almost 95% of the mass sitting on the launch pad has to be propellant, which means that all of your structure can only be about 5%. Now, if we could make super strong, super light structures,
like an eggshell,
then in principle we could get to orbit without staging. That was the dream. Now that's the first thing you learn in Rockets 101 is why you can't do single stage to orbit. It's because right now we don't have the technology.
Well, and see,
to do that.
many people have studied single stage to orbit. In fact,
NASA tried to build one.
We tried to build one,
and we failed.
And we failed. Well, what they say is really what you need is to be as smart as or as high tech as an eggshell. Be able to make the structure as thin as an eggshell, hold all the fluid in it, and have very low density.
Someday
we will have single
maybe
stage.
we'll do it.
So that was the structural limit of the liquid fuel tank, and the rest of it was compensated by solid rocket.
Yeah.
Is it?
Yeah, basically, when you by using the boosters, or in a more traditional rocket, a first stage. Once you've exhausted the fuel, then you drop all of that structural mass, and so for the second stage, this initial mass becomes much lower.
That's right.
And so you can get a lot more payload.
Let me just add one thing. The other thing that's interesting is that if you go back to Apollo, during Apollo there were 3 ways to go to the moon. One was direct. Von Braun wanted to build a large vehicle called the Nova, where you actually lifted off from the Cape and sent the whole vehicle right to the moon. The other was to do Earth orbital rendezvous, and the other way was to do lunar orbital rendezvous like we did. It turns out that Nova vehicle was so big, had to be so big, that was ruled out. So we wound up with Earth orbital rendezvous or lunar, and finally went with lunar orbital rendezvous. Yes, sir.
How much did a role did geography play in the design considerations? Because I mean, just looking at that, I mean, you have to have the external tank separated at a specific
A lot,
time
quite a bit.
Not hitting, Africa. But
Yeah.
we're talking about launching at Vandenberg. I mean,
Well, launching Vandenberg, originally we thought about launching out of New Mexico too, but you did. I don't know. But you had to have that.
Yeah, I mean, actually, when you're doing flight design, one of the depending on whether you're going into a due east launch to go into a 28-degree orbit or a high inclination orbit, you actually the placement of the external tank re-entry is a major factor
we spent a lot of
in flight
time
design, and in fact, often the trajectory has to be shaped. To be not quite as efficient as it might otherwise be, because you have to control the landing of the external tank.
But your question is a good one. I did some consulting for a company after I retired, and we were looking at a commercial launch vehicle, and we were trying to launch the vehicle out of various places in the United States, and it's very difficult to get approval because of the concerns they have for that. For types of failures or anything that you're going to do. Yes, sir.
I'm not sure why I thought this, but I was under the impression that the external tank burned up in the atmosphere.
No.
And didn't hit down. So there's like 100 fuel tanks.
It breaks up.
It breaks up. It doesn't come down as one big glob. It does.
Some of it burns up, but some of it does get back to the ground.
Yeah.
Okay. Is there any talk about a need to clean up all of that?
Well, they haven't yet. No. I'm not an astronaut.
That's mainly aluminum.
Yeah.
Remember, the liquid hydrogen, liquid oxygen inside evaporate, and they're non-toxic.
The question that Dr. Young asked about the solid rocket booster environmental problem is a real problem that had to be solved, or had to be. The other problem I had, I worked on trying to get the Galileo cleared because it had a radiothermonuclear generator on it. To get that cleared going into orbit is a big job. I worked on that, and I thought I'd never finish it, but we finally got it cleared. But it was a very tough job to get RTGs cleared to be launched.
Yeah, I don't remember specifically all the noxious chemicals that come out of the solid rocket boosters, but it's pretty nasty stuff.
Yeah, it is.
I remember one of my launches, the families and guests are taken to a launch site viewing area about 3 miles inland from the launch pad, and it just so happened that the wind was blowing onshore that day. It was an afternoon launch, and my brother is a real space nut, and he always liked to watch as the rocket went, the whole, after about 7.5 minutes, it just sort of disappears over the horizon. But after about 5 minutes, the solid rocket exhaust was actually approaching the spectator area because of the wind blowing in. They made everybody get on the buses and drive them away. so that nobody got injured. And my brother was really annoyed because he didn't want to leave.
If we have time, during my lectures, I'd like to talk to you a little bit about the Challenger accident. Talk to you about the O-ring seal. I would like to talk to you about that because I don't want to sweep those things under the rug, but I'd like to talk to you about that because I've got my own thoughts on the problem, and I'd like you to hear it. Okay, any other questions on the mission profile? What should we keep going or?
Okay. Tell you what, let's take a 2-minute break. Stand up, turn around. An hour is long enough time to sit for a bit.
Good, thank you.
I'm assuming that everybody is aware that the Russians at one time had a space shuttle program, and they manufactured a vehicle which looked almost identical, not exactly, but almost identical, and it was no accident because they used our plans.
These plans used our thermal protection system
Right.
too.
And they only ended up flying it once, and they actually flew it unmanned.
They flew it unmanned.
Despite a little bit of nail biting during the landing, they did recover it successfully. And then they discovered just what we had discovered, was that this is a lot more expensive to operate than they had anticipated, and they had a lot less money than we did, and so it basically never flew again. They had crews of cosmonauts who had been training to fly the Buran, but there were actually two differences. The first was that they put the engines on the external tank. I think that this did two things. First of all, it did improve the performance. And also the Russians were turning out, they turned out engines on assembly lines, basically. They turn out a tremendous number of rocket engines, and I guess that from their point of view, and I don't know the details of the performance of their engine, how their main engines compared to ours. I think they actually had 4 engines, if I remember.
Did they use liquid hydrogen?
I think they did, yeah.
So what would be the simplest of line? Do they have an advantage in terms of getting back if it doesn't?
The orbiter was just a glider, and it was no difference. It was an unpowered glider. The other thing that they did learn one thing from us, that when you have a delta wing vehicle, you're very, very sensitive to the center of mass of the system. And it was a problem because you have to, the orbiter, when it flies back through the atmosphere, flies through a flight regime. It hits the top of the atmosphere at Mach 25, and then it flies all the way down to subsonic. And the control characteristics and stability characteristics change throughout that flight envelope, and we'll have a lecture specifically on the aerodynamics of the shuttle. But it turns out that the shuttle is extremely sensitive to the forward CG, and I think it was around the Mach 3 flight regime. If you're just an inch or two forward of a critical area in the CG, you can lose control. And so we actually, on many flights, they always do a weight and balance on the shuttle before launch, and on many flights we've actually had to put lead ballast in the aft engine compartment of the shuttle just to get the CG far enough back to get Mach 3 stability. I hate to tell you how many tons of lead we've launched into orbit over the course of the shuttle program because of the CG. And if you look at the delta wing profile of Buran is slightly different from the orbiter, because I guess they learned the lesson, and so they were not as sensitive to the CG. But of course, once you build an orbiter, you can't really change it, and so we were sort of stuck with it.
One of the other concerns to add on, one of the other concerns was that having the orbiter with the thrust behind the orbiter and this large mass in the tank, you could get what you call pogo. You could get a pogo type of activity, a pogo. And so one concept that Max Vijay had early in the program was to have a swing engine, actually have the engines fire on the back of the tank, and then actually, when you get ready to separate the tank, swing the engines back into the orbiter and bring them back in the orbiter. That was we threw that out. That was a little complicated. Mechanisms, you're going to have a discussion on mechanisms and mechanical systems. And mechanical systems, everybody can design them, but everybody has a hard time making them work. There's everybody. When you put up a mechanism, when you put up an electrical schematic, everybody accepts it. When you put up a mechanical drawing of a mechanical system, everybody's got an idea how it's supposed to work. Okay, let's move on. I got some pictures now just to show you. You've shown the profile, and then of course you've seen the vehicle when it gets to a rollout of the assembly building. There it's stacked, and then it's on a crawler. This crawler basically was used for Apollo, and the crawler takes the vehicle out to the pad.
Just one thing so that people notice the difference here. Can anyone Is anyone familiar enough with Apollo to be able to say what the fundamental difference is with the crawler mechanism here and the crawler and the pad?
Not sure.
Well, if you look at the picture of a Saturn rocket being rolled out on the crawler, the whole launch tower was on the crawler.
Oh, that's right, yeah.
And so they rolled the whole thing out. With the shuttle, it's a little different. I'll be bringing in some pictures at some point to show you some of these details, but they cut off the top part of the Saturn launch tower because the shuttle stack isn't quite as tall, and they added a movable what's called a payload changeout fixture. And so once the shuttle actually gets on the pad, there's actually railroad tracks here.
Is this a better picture of it? Just a better picture of it?
Oh, okay, yeah. This whole enclosure rolls over and forms a kind of a hermetic seal around the shuttle so that you can open the cargo bay doors, which, by the way, can't support their own weight in 1G, so you have to put an external strong back on them. And in the meantime, you put the payload that's going to be installed has been, you have this payload canister here, that's installed in the changeout room, and then it's swung over, the doors are open, the payload is installed in the bay, and then this forms a protective enclosure over the shuttle, and it's not swung back usually until the day before launch. So that's
see, now this is again another detail in systems engineering. You went from that schematic or that little plan form of the orbiter, and you did iterations of the size, and then you had to do iterations of the launch complex, how it was going to be put payloads in, and that's all systems engineering. That it's certain levels of systems engineering.
I mean, it's very easy to say, well, we'll put the payload in on the pad, but the actual development of the mechanisms to do that is extremely complicated, to say nothing of which, I mean, what kind of amazes me is that it has to be done essentially in a clean room environment.
Right.
So, you're up there crawling around the pad and inside the payload changeout room in white coats, bunny suits, and gloves on. And outside, the wind is blowing, and it could be raining. There's sand blowing by, and so the whole thing has to be done in a clean room environment. But it's on the scale of a naval shipyard. Yeah. This is a huge vehicle, so it's really a challenge.
Of course, and that's one of the reasons, in all honesty, why the cost per flight has gone up. The original concept. When Dale Myers was Associate Administrator of Manned Spaceflight, I went up to him seeing I was the Orbital Project Manager, and we concluded this is going to be very simple. We were going to make very standard payloads. You went, put the payload in, fixed it in. We were going to launch it, deploy it, come back. If the computer failed the computer on the pad, we'd go anyways. We wouldn't replace the computer. Of course, that all changed. The missions became very complicated, and we didn't do that. So that is one thing. That's another important point, though. You better be sure when you get to be a project manager or manager, understand your requirements, understand your customer's need. But the ground rules change, your performance is going to change. So you need to understand that. Any other point you want to make, Jeff? Any other question? I just got some other pictures that show you. Here's the liftoff. As you see, the liftoff, everything burning. Nice birds out of the way. I guess have we ever had a case where we hit a bird on launch?
Yes, I believe we have.
Of course, one of the things you do in the orbital windows, one of the things you do is you fire dead chickens into the window to see if you can break the window in the system. I think they do it in aircraft also.
Yeah, and we actually did. I remember one simulation where in the simulator, right at liftoff, the instructor came in and threw a rubber bird in the commander's lap and said, "You've just been incapacitated by a bird strike." And so the co-pilot had to take over the flying of the shuttle. You should realize the Kennedy Space Center is actually a wildlife sanctuary.
Yeah, they do.
And so there's a lot of birds. It's there's a national wildlife sanctuary, park rangers, and
a lot of eagles.
And there's eagles in the nest. There's a lot of turkey buzzards, and before there's a landing strip that's right in the middle of the bird sanctuary, and so often before the shuttle gets ready to come in, they'll send planes to sort of buzz the runway and scare the birds away. They also had a problem at one point with woodpeckers, excuse me. Woodpeckers were decided that the external tank insulation was a good place to find bugs, and so this is it sounds funny, but think of what that actually potentially could mean. And they had to go down, and they had loudspeakers and stuffed owls and everything, which they ended up putting around to scare away the woodpeckers. So there's these are things, again, which I think the original systems engineering never took into account.
We're worried about F equal MA. And there's a typical deployment of, I believe that's a PAM, if I'm not mistaken, typical in a payload assist module to get the shuttle payload into orbit. Here's a picture of the crew at their station with their CRTs. And of course, then you deorbit and enter. This is of course not a real picture, but that's. Do I have that right? That's right. And then, of course, landing on the runway. So that's a typical profile that we've gone through in terms of showing. Now, let me talk a little bit more about systems engineering. When I took over in August of '72, we had what we called Space Shuttle Orbiter Management Reviews. That's North American. And this was one of September 1972. And I think it might be interesting to look at the agenda in September of 1972, what we were talking about. And here was the agenda. I'm not going to go through all the paperwork, but here was the agenda. Basic resizing of the vehicle because of certain problems we had in the iteration. Cabin configuration and docking location. The Space Shuttle Main Engine Interface Control Document. Turns out interface control documents are probably one of the most important systems integration tool, because the interface control document defines how you're going to put the main engine into the orbiter. What is an interface? An interface could be how this plug, if you got a plug in a socket, it would be bad if you couldn't plug that in. But that's an interface. When you change your tire, if those bolt hole patterns don't match, you'd be very frustrated. So that's an interface. So interfaces can be as simple as that, or they can be very, very complicated. So this is the SSME interface control document, how we actually get the main engine in terms of mechanical propulsion put into the orbit, into the orbiter. Integrated ascent control, abort requirements. And now we're talking about just procurement, RCS and OHMS procurement. Service, the rocket motors procurement package, avionics definition, leading edge TPS, and emergency egress. So these were some of the problems we started talking about. Now these are lower level systems engineering problems, but they are systems engineering to make the definition of the total launch configuration. Here's an interesting chart. This is dollars. And why this is interesting is that you see on this chart the proposal, Rockwell's proposal. These are $1 million, $123 million the first year. Well, when I became Orbiter Project Manager, that was Rockwell's proposal. The first thing they did to me, they told me I only had $73 million that year. So I had to rephase the whole program. I had to rephase the whole program to fit the funding curve that the Office of Management Budget gave me. So this was a major perturbation. When you do that and you don't get your money as the proposal, it turns out to be a cost increase. Right away, we went a little bit cost increase to 4.6, but as you don't get the funding requirements, you then essentially lose your momentum, you lose your schedule, and once you lose schedule, you start costing. As Dr. Hoffman mentioned, you have the three-legged stool of cost, schedule, and performance, and that is a continual trade-off as you go through a systems engineering program. And the things you have to look at, the things that cause program managers, project managers to lose their job is, first, you're going to recognize that you have a weight increase in the vehicle. Whatever you build is going to cause to have your weight increase. The next thing you're going to have is a schedule slip. And then when you put those together, you're going to have a cost increase. And then you're going to have technical problems. And those are disastrous cases for a project manager. Those are reasons to fire somebody. Luckily, I made it. I made it because of a man that you're going to hear talk, Chris Kraft, because he was my boss, my immediate boss. And he ran interference for me. And you're going to hear Dr. Kraft talk. And he's a good man to have on your side and run interference for you. So you're going to hear him talk. He's a great guy, and he's going to tell you what he thinks. And he'll tell you what he thinks. But that's a little bit about cost. Further systems engineering questions in the orbital management review is orbital maximum wing size. And ATP is our authority to proceed. Wing size is very important. You got to get that model, the aerodynamic model, the wing loads squared away. We said no major line change after program requirements review. Controlled ride weight was 170,000 pounds, including margin.
And I don't think we made that, did we?
No, we didn't. No, no, we didn't.
Or like 200,000.
Yeah. No ejection seats on vertical flights. Top located docking port. Wing area for landing speeds of 150 knots. Wing stiffness criteria, flutter margins, control effectiveness for entry and ferry, Elevon design concepts, and integral cantilevered crew cabin. These were some of the systems engineering problems that had to be resolved before you could start manufacturing. One of the interesting things, I forgot who was head of the astronaut office at the time, but I don't know if it was Brandenstein, I don't know who it was. Anyways.
At which time?
Well, about the time of the design of the shuttle. About this time when we were.
Al Shepard was.
Was it? I forgot. I asked somebody.
I remember when John Young took over.
Yeah, I forgot who I asked, but we were trying to get the cockpit laid out. It was very important to get the cockpit laid out, and I wanted the crew to have their inputs on how they wanted the cockpit. You want the crew to be a part of laying out the cockpit. So I called the head of the astronaut office over, and I said, we need to lay out this cockpit, and you need to come back to me with a decision of how you want the cockpit. He said, I can't do it. I've got 100 astronauts over there, and they won't agree. I said, I'll tell you what you do. You tell them that I'll give them 2 weeks, and then I'm going to do it. And that really scared them, because I didn't know anything about laying out a cockpit, and we had the cockpit laid out. So that's sometimes you have to use some type of management techniques. Okay, now we're going to get more into the details of what you're going to hear in some detail. I'm going to start it off a little bit. Here are basically the hardware subsystems. You're going to hear a technical briefing on the thermal protection system and the structures. You'll see in your syllabus when that is, but you're going to hear a very detailed discussion of the thermal protection system and structures by Tom Moser, who actually did the work. He was actually what I call my subsystem manager on the shuttle in the early days of the program. You're going to hear a technical briefing on the space shuttle main engines. A very detailed briefing by J.R. Thompson. J.R. Thompson, a little background about him. He was he was project manager of the main engine at Marshall Space Flight Center. Then he became director of the Marshall Space Flight Center. Then he was deputy administrator at NASA. Now he's vice president of orbital sciences. You're going to have a detailed briefing on the hydraulic system, the auxiliary power system, fuel cells, orbital maneuvering system, and the reaction control systems. That's going to be by Henry Pohl. Guidance navigation control is going to be by Phil Hattis from the Draper Laboratories. Environmental control and life support in the crew cabin And that's going to be a man that's currently working at the Johnson Space Center, Walt Guy, who actually did this job for the Apollo. Most of these people, by the way, did the same thing for the shuttle, the Apollo, that they did for Shuttle. So very similar jobs. So you can ask these people about the Shuttle, about the Apollo program. Landing and Mechanical Systems by Al Levere. Communications, electrical power, we're really not going to brief, although we'll talk electrical power when we talk fuel cells, but we're not going to really have a discussion on communications and fuel cells. And then we're going to have some analytical studies. We're going to have analytical studies on aerodynamics and aerothermodynamics. These will probably be, if you have any more, these will probably be detailed technical discussions when we get in aerodynamics and aerothermodynamics. And again, these people did the same on the Shuttle as they did on Apollo as they did on Shuttle. So that's going to be your details of what you're going to see. What I'd like to do now, with the few minutes we have remaining, is talk to you a little bit about, give you a little bit of flavor of some of these subsystems, a little bit more detail than that we've previously given you, but not as much detail as you're going to see. So let's start off a little bit with the orbiter and just show you what the orbiter looks like. And talk a little bit about some of the subsystems in the orbiter. The forward reaction control system is up in the forward nose of the vehicle, and then you have the reaction control system back in what's called the OMS pod, the orbital maneuvering system pod. You have reaction control systems here and here. So that's the reaction control systems. You have your orbital maneuvering system back in these OMS pods. Of course, you have the main gear, main landing gear and nose landing gear. The wing, fairing, and the leading edge, which is the carbon material. This wing leading edge is carbon material. And the side hatch, and the overhead windows, and then the side windows, and the forward windows. The payload bay. The payload bay is interesting. Payload bay doors are made out of graphite epoxy. Graphite epoxy is originally made out of aluminum. We made it out of graphite epoxy because of the weight growth. We could save quite a bit of weight if we went from aluminum to graphite epoxy. So that was the largest, probably at that time, it was the largest composite material used in an airplane. It was made out of graphite epoxy. And then the main engines, of course, are in the aft end of the orbiter. And then you have the vertical tail, the stabilizer. And, of course, you got your elevons. And you got the body flap. The body flap was actually put on originally to deflect some of the heat from the engine, but actually it turned out to be a control surface also. So it actually turned out to be both functions of a control surface. So that's sort of the layout, and you can visualize where you use these systems, these active systems. The reaction control system is used primarily in orbit and getting ready to deorbit. The OMS is used to help you get into orbit and get out of orbit, or maneuvering you want to do. The body flaps and the elevons are actually used primarily during entry, a little bit during ascent, during entry. We do use the RCS system a little bit during entry in the high altitudes of entry. It's used use the RCS system, but eventually during entry the loads become so high, the RCS system, or reaction control system, does not become very effective. I guess that's about all I want to say. Any questions on that? Yes, sir.
I was wondering why the nose gear was so short.
Well, it saved weight, but making it shorter. It was easier to put in and saved weight, and it gave you a.
And I think also when you land, by having the nose down, you actually have an aerodynamic force pushing
down
the orbiter down on the runway, which increases your stability. And since you don't have to worry about, eventually taking off, like Professor Cohen said, if they had wanted the shuttle to be able to take off horizontally from the runway, they would have had to raise the nose.
Yeah. Yes, sir.
Is it under-designed deliberately just to save the weight?
Well, when you say under-designed, I mean, it was. I would call it a minimum design. It was not. I mean, if it were under-designed, it would break. I mean, there are landing limits.
Yeah,
as I said, the orbiter for a planned nominal landing. And you have to realize there are different kinds. There's emergency limits and limits for nominal operations. You can take off with 65,000 pounds. That means if you have a launch abort and you have to return and land with your payload, you will be landing with 65,000 pounds in your. But you don't plan to do that. That's a one-off deal. If you're planning to do it, it means you can do it over and over again, and then the limit is 35,000 pounds. They don't build it like a Navy carrier landing airplane, I'll tell you that.
Not just maybe, I always found the tire was just really small.
The tires are small.
Small. And they have no tread. They have no treads either.
Yeah, and the brakes were small. Actually, the original brakes were under-designed, and we kept having brake failures.
And that's why we put in fact, I took the drag chutes off, and then we put them back on.
Right.
I took them off because of weight, and we put them back on. Tires are very interesting. We're going to have a very detailed discussion on tires, but tires are very, very complicated. You know, you think by putting more treads on the tire, more plies on the tires, you make it stronger, but not necessarily, because when you cycle them, they get hot, and the more plies tend to hold the heat in, and it weakens the tire. So tires are not a very simple thing to design.
So you used only once then?
Yeah. No, I think we used tires about 5 times. I could use them up to 5 times.
The brakes are used 5 times. I don't know about the tires. I don't know.
I don't know. Let me you talk about weight and margin. Let me go back to Apollo. We had Apollo designed, and we found that on the lunar module, taking off from the lunar surface, it was too heavy. We couldn't lift off. And the engines were already built, the tanks were already sized, and we couldn't get off the lunar surface. And that's not a very good deal. The astronauts didn't like that too well. So what we did is, George Lowe was the program manager at the time. We were spending, in those year dollars, $24,000 a pound to get weight out of the lunar module. And they scraped, they did everything they could to get any.
That was a bonus to Grumman, is the way I heard.
Well,
is that correct?
It was bonus to Grumman.
You were basically offering them $24,000 for every pound that they could scrub out.
Because we had no way of getting off the surface, we couldn't resize the engine. The engine was there.
They were literally in there with emery cloth, shaving down the aluminum from the inside.
So weight can be very critical.
I don't think most people realize how close the margins were there. I mean, the lunar module was only certified for, I think, 5 pressurizations?
Yeah, something. Yeah.
And then it was beyond its structural
My statement to many people: the next time we go to the moon, we're going to find out how hard it really was. Because to tell you the truth, we went to the moon. We went to the moon with one computer in the command module and service module, and one computer in the lunar module. Although, excuse me, we did have 2 computers in the lunar module. We had the MIT computer, and then we had a strap-down system built by TRW. So that's an interesting point. Let me now. I think somebody asked a question last time. Let me talk about the aft end of the orbiter a little bit, because we did not have CAD/CAM systems at the time. We did not have CAD/CAD systems. And let me show you a little bit. These are some pictures. These are some pictures taken. This is, I don't know what vehicle it is, but that's the aft end of the orbiter going together. That's where the big engines go into. This looks like it's going to take off. If you crawled in the back of the aft end of the orbiter, there's plumbing, there's wiring, there's structure. Now, had we had computer-aided design at that time, I'm convinced we would have a much neater, better design than we have today. We had to mock everything up. We mocked it up, and we changed it. People bumped their heads on it. But this is really, you go back in the aft end article, you wonder how they can do anything with it. But that was done because we did not have computer-aided design. We couldn't build like like airplanes now have virtual mock-ups. You can actually build a virtual mock-up right on your computer. We didn't have any of that. And this, again, is just to show you just what the crew module looks like in a structural point of view. That was the pressure vessel. That's basically a pressure vessel going together, and there were the windows But the thing that's interesting about that, it had very intricate welding techniques. And these techniques were very good, and actually it proved to be a very, very satisfactory design of a pressure vessel. I would like to now talk a little bit about a couple of subsystems that you're going to hear much more detail about, but now venture into some subsystems and tell you a little bit about them. It's probably going to be the thermal protection system and the guidance and navigation system. Talk to you a little bit about that. Here is a chart. This is an old chart that shows, now unfortunately I use English units, maximum heat rate in BTUs per foot second squared, integrated heat load, and radiative equilibrium temperature. And that is, and then you see the Apollo return is number 4. And the Apollo design was about 100 BTUs per foot squared integrated heat load, if I read the chart right, and about 300 BTU, and about a heat flux of about 300 BTUs per foot squared second, with a radiative equilibrium temperature of about a little over 5,000 degrees Fahrenheit. Now the arbiter, now we used on Apollo, that was our baseline, we used a ablative heat shield. Now the ablative heat shield has a density of about 130 to 140 pounds per cubic foot. Now, and it's not reusable. On the shuttle, shuttle was about 40,000 BTUs per foot squared integrated heat load and 50 BTUs per foot squared second for heat flux, with a radiative equilibrium temperature of about 3,000 degrees Fahrenheit. Now we had at that point in time, we had to come down from our baseline knowledge of an ablative material to what we could use and make it reusable.
And light.
And light. And there were several competitors at the time. One was a metal insulation, Rene, Rene, I believe 41, shingle type material, very thin, make it very thin, very high temperature, and it had pretty low density. And then, of course, there was the ceramic material, or the so-called tiles, which was basically a ceramic material. It's made out of silica. In fact, interesting enough, it's made out of what we call gopher sand that comes from Minnesota. Why is it gopher sand? I'm not quite sure, but it's got very high pure silica content. And you make it into a mulch, and then you actually bake it, and it comes out in these blocks, tiles. And of course, tiles sometimes are hard to bond to the vehicle. I mean, how many people knew that tiles were hard to stay on the vehicle? Well, I was the Arbiter project manager, and my hometown is San Antonio, Texas. So we'd go back to San Antonio to visit my family. My little aunts would say, their nephew was in charge of the shuttle program, and he was having trouble making the tiles stay on the vehicle. They couldn't understand it because they had tiles in their kitchen, in their bathroom, and they had no trouble at all having those tiles stay on the vehicle. So they couldn't understand why I was having so much problem having the tiles stay on the vehicle. But so we had a problem. What would we use? And we came up, and there was two competitions on it. One was the competition from two of the research centers. The Langley Research Center wanted to go with the metallic version, and the Ames Research Center wanted to go with the ceramic version. And we at JSC were trying to figure out which one to go with, and we decided to go with the ceramic version. Of course, Tom Moser is going to go this in detail because Tom, when you hear Tom talk, because he was the guy really in charge of it. But just to give you a little background, and he'll go through more details of it, but just to give you a little background of it, the problem we had with the tiles is that when you bonded the tiles, of course they were ceramic. They were basically a ceramic material. And when you bonded the tiles, forget about this layer called densified for a moment. When you bonded the tiles to the room temperature vulcanizing material, which is basically a glue, high temperature glue, to the strain isolator pad, you got stress risers set up, and the tile became very weak. It broke really at the bond line of the tile because it became very weak. It broke. The stress risers were such that because it was ceramic, it broke at the interface. We had one very clever engineer, that saved my life, my day. because tiles were falling off, and I couldn't get the vehicle built. He said that if we densify about a lower quarter of an inch of the tiles could be anywhere from 2 inches to 4 inches thick. If you densified the low quarter of an inch, by that I mean put liquid glass inside that tile, the bottom became like a really hard surface, no stress riser. You could bond it like this, and basically have the inherent strength of the tile. It no longer broke at the bond line; it broke at the tile, which had a very high load. So we really did. So after we did that, we really did solve the tile problem to a large extent. So that was the day that we really solved the tile problem. But it was so. I remember this so distinctly that we were doing all these tests and all these analyses, and all of a sudden they called me one day and said, "Aaron, we're just doing a very simple flat-wise tension test, and tiles are just coming off just like everything off the vehicle." So that is what saved the day.
I think it's a good another good example of problems in system engineering. If you just leave it there for a moment.
Sure,
because,
sure.
We worked so hard figuring out how to make these tiles. I mean, and they're extraordinary. You can take one of these tiles, you put it put one side of it into a kiln, heat it red hot, and you could hold the other side of it in your fingers. I mean, that's how good the insulation is. And I guess everybody just sort of figured, we know how to glue things on.
You brought up another very good point that I left out. The problem is we spent so much time figuring out the efficiency of the tiles to do the thermal protection. In other words, this is fantastic tile. It's about the density of, it weighs about like balsa wood. It's like balsa wood. So it's anywhere from 10 to 12 pounds per cubic foot, compared to 130 pounds per cubic foot. It can take a higher temperature, is ablative material, and be reused. So it answered all the questions we had about thermal protection. What we didn't do, though, is figure out how we were going to attach it to the vehicle.
And everybody, I think, just assumed. It's almost like your relatives. We glue tiles on the bathroom all the time. Anybody can gluing stuff on.
But we really did a bad job. In fact, that's an example I use in my course at A&M. Is we come up with a function structure. What functions does this have to perform? Well, it doesn't actually have to thermally protect the vehicle. It's got to stay on. And we forgot about the staying on part. We talked about the thermal protection part. And this thing is so good, its thermal diffusivity is so good that, I mean, like Professor Hoffman said, you could get the surface temperature to 2,000 degrees Fahrenheit and hold it in the palm of your hand. And so it turned out it was a very, very good solution, but we almost blew the day by not coming up with this design.
Why does it have to be individual tiles rather than big long panels?
Well, because of the difference coefficient expansion.
Now, and that's the point of this strain isolation pad. And it's another interface problem, which is part of the systems engineering. The structure of the shuttle is aluminum. Okay? Thermally, it expands and contracts by several inches every time you go from night to day. I mean, the orbiter, we've done these measurements. I mean, one side of the orbiter is pointed towards the sun, the other side is cold. The orbiter actually bananas by a couple of degrees. And they did thermal tests in some of the orbital flight tests where, the payload bay, the clearances could change by a couple of inches depending on the thermal conditions, and designing mechanisms to latch them closed with those tolerances. So the orbiter is flexible and it expands and contracts as a metal. The tiles don't. They're rigid, and so if you have too large a tile area, the aluminum is going to bend under it, and the tiles will crack. And even with the small tiles, between the aluminum and the tile, there's this strain isolation pad, which is like, think of it as sort of like a felt type material. So it kind of eases the interface between the two.
Of course, then if you look at the tile installation on the vehicle, and that's in between the tiles. You remember on the last mission we went EVA to fix the gap fillers, but gap fillers between each one of those tiles, mainly for problems during liftoff to keep the tiles from vibrating and damaging each other. And those gap fillers, I had my concern about going EVA to fix it, but on the other hand, once you see the problem, you can't let it go, so you got to do something about it. So they went EVA and pulled the gap fillers out. But those are the tile installations. But your questions are very pertinent. Why so many? And that's the reason. It's because of the coefficient expansion. Then you put gap fillers in between those tiles to keep it from damaging during liftoff. It turns out, though, it does turn out that one of our biggest concerns was going to be the how fragile the tiles were. And it turns out they really aren't that, they really turn out to be a pretty good system. We were concerned about losing a tile and then getting heat and having an unzippering effect where you lose a bunch of tiles. And we really, alleviated the problem. I'll tell you another funny story, and then I guess we can quit. This is probably not so funny, but it was a story anyway. So, I forgot what mission it was. But what these tiles are, they are actually waterproof. We actually put Scotchgard on them because the waterproofing is in the tile, and after a certain mission, the waterproofing boils out. So we had to waterproof the tile.
STS-4 was the hailstorm.
Well, I don't know which
that was the first one where they recognized the problem.
Well, anyways, Rockwell International, it was my contractor. Rockwell International, the head engineer at Rockwell, was a brilliant guy. But he ran a test where he put a tile panel, densified tile panel, in a bucket of this Scotchgard, or this rain repellent material. And he called me about 11 o'clock at night, and I was getting ready to go in because they're getting ready to retro fire and land. He said, "Aaron, we just ran this test, and all the tiles came off." I said, "What do you want me to do with that information? We're getting ready to make the deorbit burn." I mean, they were coming down. I said, "What do you want me to do?" He said, I said, "That was sort of a dumb test, wasn't it?" I said, "Is that what happened on the vehicle? Did you actually put a bucket of the tiles in a bucket of water repellent material?" He said, "No." I said, "Well, that's a dumb test." I took it upon myself, after talking to the man you're going to hear, Tom Moser, what do we do with it? And we didn't tell anybody. Now, I took a big risk on that, but what could you do about it? There was absolutely nothing you could do about it on that test. So that is an interesting case in discretionary project management. But you'll hear more.
Let me just mention the question of waterproofing, because again, that was something that I think at first slipped through the systems engineering, and it was the fourth shuttle flight, STS-4. I was down at the Cape for some other activity. The night before launch, they had rolled back the payload changeout room. The whole shuttle was exposed. Well, a thunderstorm with hail came through, and it pelted the bottom of the shuttle. There were pockmarks all over it, and of course it was raining, and people realized that the tiles actually were absorbing material. The outside of the tile is kind of impervious, but once you crack that, the rain can get in. And they actually they brought a tile expert down from the Cape, and they did some calculations, and how much water. I mean, I think we ended up carrying. It was an early flight, so we didn't have a maximum payload, luckily, because we ended up carrying. They figured a few. Probably a few hundred, maybe over 1,000 pounds of water into orbit. And there was so much water in the tiles that the orbital dynamicists were able to measure the perturbation of the shuttle's orbit because of all the water that was evaporating. And of course, it was evaporating from the bottom, so that it effectively was asymmetrical and had a propulsive force. And after that was when they came up with the idea of Scotchgarding. And if you look closely at each of the tiles, there's a little hole where every tile before every flight, they go through with a hypodermic syringe, and they just inject a little bit of Scotchgard. And you think how critical it is. You've got over 30,000 tiles. If you add 1 ounce to every tile, you do the math. That's a lot of extra weight. So you want to put in as little possible Scotchgard, but enough to do the job.
The reason why you bring up this subject, this might be a very good subject for you to decide to redesign. You might think about what are the technologies, what are the differences, how would you do it differently? Because their technology has changed, and you might, that's why I brought this one up. And you'll hear much more detailed discussion about Tom Moser, but you might think about this as one of the subsystems to look at. I guess that's all for Dave.
Okay, we'll see you on Thursday.